Rotor Related Fault Conditions in Electric Motor Analysis, Detecting and Diagnosing Rotor Issues for Motor Reliability. Rotor-related fault conditions, scope and importance. Rotor-related fault conditions represent a critical category of defects in AC induction motors because they directly influence electromagnetic forces, vibration behavior, thermal performance, and long-term reliability. Unlike purely mechanical faults such as bearing damage or misalignment, rotor faults often manifest as a complex interaction between electrical and mechanical phenomena. These faults can initiate subtle changes in air gap geometry, current distribution, and magnetic flux, which then translate into characteristic vibration and current signatures. Early detection is essential because rotor faults tend to accelerate once initiated, especially under high load or frequent start-stop operating conditions. From a reliability engineering perspective, understanding rotor fault mechanisms enables maintenance teams to distinguish between electrical root causes and secondary mechanical symptoms, avoiding misdiagnosis and ineffective corrective actions. This presentation focuses on the most common rotor-related fault conditions encountered in industrial motors, including eccentric rotors, thermal rotor bow, broken or cracked rotor bars, lamination problems, and loose connectors. Each fault is discussed in terms of physical cause, characteristic vibration or current signatures, and recommended diagnostic techniques. Emphasis is placed on practical condition monitoring using vibration analysis and motor current signature analysis, MCSA, which together provide complementary insight into motor health. By correlating frequency domain indicators such as line frequency harmonics, pole pass frequency sidebands, and rotor bar passing frequencies with operational data, engineers can confidently assess rotor condition and plan corrective maintenance before catastrophic failure occurs. Eccentric rotor, variable rotating air gap. Representative vibration spectrum and rotating air gap illustration associated with eccentric rotor conditions. An eccentric rotor condition occurs when the rotor's geometric center does not coincide with the stator's magnetic center, resulting in a non-uniform air gap that varies as the rotor turns. This variable rotating air gap produces unbalanced electromagnetic forces that act radially on the stator and rotor, generating a pulsating source of vibration. Eccentricity may be static, dynamic, or a combination of both, depending on whether the minimum air gap remains fixed or rotates with the shaft. From a vibration analysis standpoint, eccentric rotors are characterized by elevated vibration at twice line frequency, 2 times LF. Often accompanied by pole pass frequency, PPF, sidebands around 1 order running speed and 2 times LF. The pole pass frequency is defined as the slip frequency multiplied by the number of poles, and because slip frequency is typically small, high-resolution spectral analysis is often required to clearly identify these sidebands. Radial vibration measurements are most sensitive to this condition. Eccentricity can be caused by manufacturing tolerances, improper assembly, bearing wear, or shaft deflection under load. If left uncorrected, eccentric rotors can lead to localized heating, increased stator insulation stress, and eventual rotor-to-stator contact. Accurate diagnosis relies on correlating vibration signatures with electrical data and confirming mechanical alignment and bearing condition. Thermal rotor bow due to uneven heating. Example spectrum showing thermal rotor bow signature, which closely resembles mechanical unbalance. Thermal rotor bow is caused by uneven heating of the rotor, typically resulting from unbalanced rotor bar currents or localized electrical defects. When certain rotor bars carry higher current, they generate excessive heat, causing the rotor material to expand unevenly. This thermal expansion results in a physical warping or bowing of the rotor. From a vibration perspective, thermal rotor bow closely resembles a classical unbalance condition, with dominant vibration at 1x running speed and a stable phase relationship. A key diagnostic indicator is that the vibration subsides or disappears when the motor is cold, distinguishing it from permanent mechanical unbalance. Thermal rotor bow is load-dependent and often worsens as operating temperature increases. In severe cases, local heating can be so intense that rotor bars partially melt and intrude into the air gap, dramatically increasing the risk of catastrophic failure. Engineers should compare vibration data collected during cold startup and steady-state operation to confirm this fault. Corrective action typically involves addressing the underlying electrical imbalance, such as damaged rotor bars or end ring defects, rather than performing mechanical balancing alone. Broken or cracked rotor bars, failure mechanism and symptoms. Illustration of cracked rotor bars and associated vibration sidebands. Broken, cracked, or corroded rotor bars are among the most common failure modes in squirrel cage induction motors, particularly in applications involving frequent starts, high inertia loads, or voltage disturbances. During motor startup, rotor currents are significantly higher than during steady-state operation, placing substantial thermal and mechanical stress on rotor bars and end rings. Over time, this stress can initiate cracks that propagate until the bar becomes electrically ineffective. The resulting current imbalance causes characteristic vibration and current modulation at frequencies related to slip. In vibration spectra, cracked rotor bars generate pole-pass frequency sidebands around one order running speed and its harmonics, often producing a busy spectrum with multiple skirted peaks. A distinctive phenomenon known as beating may be observed, where vibration amplitude slowly rises and falls at twice the slip frequency. This modulation is often audible and varies with load. Because these signatures can be subtle at early stages, trending over time and combining vibration with motor current analysis significantly improves diagnostic confidence. Rotor bar passing frequency, RBPF, indicators. Rotor bar passing frequency, RBPF, is defined as the number of rotor bars multiplied by the rotational speed of the motor. This frequency is normally present in vibration spectra because each rotor bar interacts with the stator magnetic field as it passes through the air gap. RBPF typically appears at high orders, often between 35 times and 96 times running speed, depending on rotor design, and is characterized by sidebands at twice line frequency. Under healthy conditions, these peaks remain relatively stable in amplitude. However, increases in RBPF amplitude or pronounced sideband activity may indicate cracked rotor bars, loose bar joints, or end ring defects. RBPF analysis is particularly useful because these peaks are easy to identify and trend over time. When combined with load data and current measurements, RBPF provides valuable insight into rotor electrical integrity and the progression of bar-related defects. Example spectrum highlighting rotor bar passing frequency with 2 times line frequency sidebands. Shorted laminations and thermal warping. Spectrum illustrating increased 2 times line frequency vibration associated with shorted laminations. Motor rotors and stators are constructed from thin, insulated laminations designed to minimize eddy current losses. When these laminations become shorted due to insulation breakdown, localized circulating currents develop, causing intense local heating. This heating can result in thermal warping of the rotor or stator core and significantly elevated vibration levels. Lamination problems are often associated with increased vibration at twice line frequency, sometimes accompanied by elevated one-order running speed and pole-pass frequency sidebands. Because lamination faults are both electrical and mechanical in nature, they can be difficult to diagnose without careful spectral analysis and temperature monitoring. If left uncorrected, shorted laminations accelerate insulation degradation and can lead to severe motor damage. Early detection and corrective action, such as core repair or replacement, are critical to preventing catastrophic failure. Loose rotor on shaft, mechanical instability. This diagram showing a harmonic-rich vibration spectrum associated with a loose rotor on the shaft. The loose rotor on the shaft occurs when the interference fit or mechanical locking between the rotor core and shaft is compromised. This condition often develops intermittently and may be influenced by temperature changes or abrupt load variations. When the rotor slips relative to the shaft, severe vibration is generated at one-order running speed and its harmonics. These harmonics can extend to high orders, indicating significant mechanical instability. The vibration response may change suddenly following load or voltage transients, providing an important diagnostic clue. Loose rotor conditions are highly destructive and can rapidly escalate into catastrophic failure if not addressed promptly. Confirmation typically requires correlating vibration data with operational events and performing mechanical inspection during maintenance outages. Loose stator windings and insulation degradation. This diagram is an example of elevated 2 times line frequency vibration due to loose stator windings. Loose stator windings allow movement of conductors and stator iron under electromagnetic forces, particularly at twice line frequency. This movement leads to increased vibration at 2 times LF and causes mechanical abrasion of the winding insulation. Although vibration severity may not increase significantly as insulation deteriorates, the electrical condition of the windings progressively worsens, eventually resulting in shorted turns or ground faults. Because vibration alone does not reliably indicate the severity of insulation damage, motor circuit analysis is required to properly assess winding health. Early detection of loose windings is essential, as this condition is highly destructive and often leads to irreversible stator failure if left uncorrected. Loose electrical connections and phase imbalance. This diagram showing vibration spectrum showing 2 times line frequency with 1/3 line frequency sidebands due to loose connectors. Loose electrical connectors can create phasing problems and current imbalance within the motor, leading to excessive electromagnetic forces. This condition is characterized by elevated vibration at twice line frequency, often with sidebands at 1/3 line frequency, 33 or 40 Hz depending on supply frequency. These sidebands are a distinguishing feature of phasing-related issues and help differentiate them from other electrical faults. Loose connections may occur at terminals, motor control centers, or within junction boxes. Prompt electrical inspection and correction are essential, as prolonged operation under phase imbalance conditions accelerates insulation degradation and increases the risk of motor failure. Integrated diagnostic approach, vibration and motor current signature analysis, MCSA. Effective diagnosis of rotor-related fault conditions requires an integrated approach that combines vibration analysis with motor current signature analysis. Vibration analysis provides insight into the mechanical response of the motor to electromagnetic and structural forces, while MCSA directly reflects electrical asymmetry and rotor defects. High-resolution spectral analysis is essential, particularly for identifying low-frequency sidebands associated with slip and pole pass frequency. Best practice involves trending key indicators over time, correlating spectral features with load and temperature data, and validating findings through inspection during planned maintenance. By leveraging both techniques, reliability engineers can achieve higher diagnostic confidence, reduce false positives, and implement proactive maintenance strategies that extend motor life and improve operational reliability. Illustration of motor current spectrum used to identify pole pass frequency sidebands.